Finally, it's my great pleasure to welcome Professor Sherrilyn Roush, former Sowerby Chair of the Philosophy and Medicine Project at King's College London, currently Professor of Philosophy at UCLA. The title of her talk, which has changed slightly, I think, from what was posted on our schedule, is Healthy Suspicion, Frequencies, Causes, and Proxy Variables.
Yes, thank you, Winnie. Thanks for inviting me. The idea behind the title is that since we can't teach doctors everything can't teach them about everything that they're going to face, I see our task as trying to train students' suspicion and plausibility meters. In my remarks, I'm going to mostly be in character, as if I were teaching a class, instead of talking about what we should be teaching them. Except that I wouldn't put this much material in one class. I'm going to begin with reasoning with base rates or frequencies, since these are a source for stereotyping and automatic inferences. Then I'll explain what I think doctors need to understand about the new biological way of defining race, and I'll illustrate how easily we fool ourselves about race. So base rates or frequencies take the following form. You have a population and two properties, say W being a woman, D being a midwife. And some members of the population have both properties, some have neither, some have only one or only the other. As of 2017, in the UK, the percentage of midwives who were women was 99.6%. We could also say the frequency of women in the population of midwives is 99.6%. And the probability that you're a woman, given that you're midwife, is 99.6%. Now, there's something puzzling about the instructions that we get about how to use such frequencies. On the one hand, we're told don't neglect base rates, always take base rates into account. On the other hand, be wary of inferring that an individual has a property just because most members of his group do. So, which is it? Well, there are two contexts where base rates are relevant. One is the context where you have a diagnostic test, like a mammogram, and the other when you don't. To interpret a test result, you always have to take the base rate into account. But if the base rate is all you have, then you should be wary of conclusions about individuals. Unfortunately, we tend to do the opposite. When we have a diagnostic test result, we ignore the base rate. And when we don't, then we rely on the base rate and make automatic inferences. If we're interpreting a diagnostic test results, we mustn't ignore base rates because the probability of disease given that test result depends on the base rate, sometimes dramatically. Suppose we have a positive test result, say for breast cancer, say a mammogram. We know the false positive rate is pretty low, say for women aged 40 to 49 at 6.5%. That's the probability you would get a positive test result even though you don't have breast cancer is 6.5%. Now here's what we often do. We say, my patient has a positive mammogram, and the false positive rate of mammograms is 6.5%. So the probability she has breast cancer, according to this test, is 1 minus that, or 93.5%. I think we find this inference inviting because we're not distinguishing the two directions of a conditional probability involving two variables. The false positive rate is the probability that you get a positive test given that you don't have the disease. So probability of plus given not B. Probability of not B given plus is the probability you don't have the disease given that you have the positive test result. So it's the reverse order. And these two terms are generally not equal. And here's an example to remind you that you already know this. The percentage of midwives who are women was 99.6%. That is, the probability that you're a woman given that you're a midwife is 99.6%. So most of that blue oval of midwives has women in it. But the fraction of women who are midwives is much less than that. Women can be lots of things, like teachers, radiologists, vice presidents-elect. So the oval of midwives is a much smaller fraction of the rectangle of women than the women are in the oval of midwives. The probability that you're a midwife, given that you're a woman, is much less than 99.6%. So conditional probabilities aren't reversible, And error rates are, for example, the probability of a positive test result given that you don't have the disease. And what we're interested in is the other direction, probability of disease or not given a test result. We can only translate the one into the other using base rates or frequencies of the disease in the population, the relevant population. We're going to do that using a grid with 100 cells. For a 40 to 49-year-old woman, the base rate of breast cancer is, say, 1.5%. This is represented by having 1.5 squares out of these 100 painted gray. We said that the probability of a positive mammogram, given that you don't have breast cancer, is 6.5%. We'll represent that by going to the squares where there isn't breast cancer, the 98.5 white squares, and coloring 6.5% of those yellow. That is 6.6 yellow squares. The false negative rate, I'm saying it's 10%, is the probability that you get a negative test even though you have the disease. For that, we go to the gray region, those who have the disease, and mark off 10% of those as black, because that's an unfortunate situation where you have the disease, but you're going to get reassurance that you don't from that negative test result. Now, what we want to know, after all, is the probability that the patient has breast cancer given that she had a positive test result. And this is the proportion of those getting positive test results that have the disease. So we read it off the diagram. We go to the set of people with positive test results, which is the 6.6 yellow squares and the remaining 1.35 of the original gray squares. What fraction of those with positive results had the disease? That would be 1.35 positive testing with the disease divided by the total positive testing, which is 6.6 plus 1.35 or 7.95. So the probability of our positive testing woman having the disease is 17%. And at that point, your whole class leans forward, like, what just happened there? So it's not that ignoring base rates is a rough approximation. No, it could be dramatically wrong. But this analysis is complicated. It takes seeing this 3 or 4 times in order not to forget the point. And who has time to do the calculation on the fly? So is there a quicker way? Yes, I think there is. When you have a positive test result, ask, what's the more likely explanation of this test result? That it's a true positive or that it's a false positive? The positive test results are the combination of the gray and the yellow areas. Which is your positive test result more likely to be? The yellows far outnumber the grays, so it's more likely to be a yellow one, a false positive. The false positives over the whole set of positives is 6.6 over 7.95, or 83%. The true positives over the whole set of positives is 1.35 over 7.95, which is 17%. Wait, those are just the posterior probabilities that you don't and that you do have the disease. So there's a rule of thumb here. If the base rate of the disease is lower than the false positive rate of the test, then a positive test result is more likely to be a false positive than a true positive. Such a test can't give you a posterior probability of more than 50% for the disease. So it's a question whether you should give that test. What if the base rate of the disease is higher than the false positive rate of the test? Here it's much higher. Fully half of the women in your patient's reference class have breast cancer. Those are the gray and black squares. The black squares are that 10% of those with the disease who get a negative test result, which leaves 45 squares for those who both have the disease and have a positive test result. The other positive test results are 6.5% of the 50 squares that don't have the disease. That's those 3.25 yellow squares. Once again, the set of positive test results are the gray and the yellow. Here, 45 plus 3.25, or 48.25. If you got a positive test result, the vastly more likely explanation for that is that it's a true positive, because those gray squares vastly outnumber the yellow false positives. They make up 45 over 48.25, or 93% of the positive test results. And that's the probability of disease for your patient. So here are the rules of thumb. If the false positive rate of the test is higher than the base rate of the disease, then a positive test result can't bring the probability of disease above 50%. If the false positive rate is lower than the base rate of the disease, then a positive test result will bring the probability of disease above 50%, as long as the false negative rate of the test is low, because every false negative is one less true positive. Now let's talk about the use of base rates in the other case when you don't have diagnostic tests. You just have frequencies like this made-up one. Let's use the phrase lifestyle problem for either eating too much or exercising too little. Say the frequency of a lifestyle problem among those who are overweight is 90%. The way this could figure in an argument is if you also know that an individual has the property of overweightness, which I've labeled F. So suppose Charles is overweight. Should you infer from these that Charles has a lifestyle problem or is likely to? Well, it's very inviting, right? Like all men are mortal, Socrates is a man, therefore Socrates is mortal. But it's nothing like that. It's not an approximate version of deductive logic because the premises give you absolutely no information about whether Charles is a representative sample. So when should we use this form of inference? Some have said, make the inference as long as you don't have any further information about Charles. But that seems too permissive. If there are true statistical generalizations involving race or gender, perhaps a product of systemic racism and sexism, this would license our judging every individual in their terms. On the other side, some have said that you can make this inference if and only if the individual was chosen from among the individuals with F by a random process. Well, that's fine for balls in urns, but no patient ever came to you by a random walk or a lottery drawing. So that rule would mean that we never are justified in using direct inference in medicine. Neither of these rules is going to work, I think. Instead, I suggest we ask, what is the weakness of this argument form? And then we could decide whether to use it in a given case by asking what the cost of that weakness is in that case. For this, think about the inference pattern as a diagnostic test that you use to decide what to think about a patient. Suppose 90% confidence in L is high enough for you to treat a patient as if they have property L. To rely on this test alone would mean that your practice is to automatically conclude a lifestyle problem as soon as you see overweight and not take it to be necessary to look for other evidence. To see the weakness of this so-called test, notice that there's only one result it can give. If a person does have property F, then it will say yes. But if a person doesn't have property F, then this test doesn't give a result. The test doesn't investigate those without F. Now, what answer would it give about someone who has F but doesn't have a lifestyle problem, if there were such a person? Maybe Charles is that person. The test is guaranteed to give the result yes, because of the property F. The false positive rate of this test is 100%. If, as a rule, you take premises of this form as sufficient to verify this conclusion, then you will have a 100% false positive rate. Given that the base rate of L in F is high, you'll only be wrong in 1 in 10 cases, but that's an average. If your first 10 cases are an unrepresentative sample, or all of them are Fs without L, then you'll be wrong in all 10 cases. As I said, these premises don't tell you anything about whether you're going to see a representative sample. The weakness of this form of argument is that it has a 100% false positive rate. So the criterion for whether to use it in a given case is what's the cost of a false positive. In this case, what's the cost of inferring that Charles has a lifestyle problem when he doesn't? Well, at worst, you'll offend him and give him nutrition and exercise guidelines that he doesn't need.
No, we have a very nice time. No.
I think we give a different answer in this case. Suppose we conclude from Cecilia's having a set of properties that puts her in class F, that Cecilia has breast cancer because of the high base rate in that class, and suppose the only treatment for breast cancer is mastectomy, then I wouldn't trust this style of argument for deciding that Cecilia has breast cancer. A false positive here would lead us to remove a breast from a woman who doesn't have breast cancer. Now you might say, well, though it could be that someone, or even many people who are overweight don't have a lifestyle problem, we don't know of any set of traits that both makes breast cancer 90% likely and also might easily be found in people without breast cancer. That seems right, but notice that that's evidence about the false positive rate of using the trait of being in class F. And if you have that, then more power to you, but you're not using simple statistical inference, so the form we're looking at here, anymore. Now this false positive problem isn't the only problem this form of inference has. Another one is that the first premise, the base rate, might be wrong. Well, you always might be wrong, but in this case, you might be wrong because of bias. Suppose we learn that the probability of colon cancer in the next year, given that you're Black, is 0.1%. Where do numbers like this come from? Sometimes they come from biased measures. What if the probability of colon cancer was measured by the number of benign polyps a person has had removed? Well, whether you have polyps removed doesn't only depend on whether you have polyps. It depends on whether you go to the doctor and whether the doctor orders a colonoscopy, both of which are affected by racial categorization. If we do statistical inference from base rates estimated on the basis of data that was affected by healthcare decisions, we will reproduce any discrimination there was in those decisions. Now, number of benign polyps removed is obviously a proxy measure, so we might naturally be suspicious of it. But even apparently direct measures can hide a bias. So suppose we have a base rate. The probability of OCD, given that a person is Black, is 0.1 of 1%. Again, these are made up. If we use this form of argument, then we're bound to conclude of any Black person that they don't have OCD, although this tendency is not made up. Apparently there is under-diagnosis of this. Now, how was that base rate estimated? Probably by looking at past data about what fraction of Black patients were diagnosed with OCD. What if Black people don't become patients at the rate that they should? And what if there's a bias that prevents doctors from seeing Black people's symptoms as fitting OCD? Well, then, if you use the simple statistical inference pattern, you're just going to reproduce that bias of your predecessors. So a base rate that looks like a relation between a race and a disease state or risk could really be a relation between a race and a discriminatory pattern of treatment or diagnosis or access to healthcare. The issue is how the disease state or risk was measured. And even a measurement method that we think of as direct, like diagnosis, could be biased. We tend to take reported base rates at face value and confine our worrying to whether we should use them to judge individuals. But the base rates deserve more scrutiny in the form of alertness to what goes into their measurement. Okay. We know that the way a person is categorized racially can affect diagnoses, treatment, and the care that she gets. But is race in the biological sense relevant to medicine? You might say, what do you mean biological race? Hasn't that idea gone the way of physiognomy? While you weren't looking, a new way of defining race biologically has been identified. It's based on measuring similarities and differences in people's DNA. One such race definition matches the 5-continent racial classification used by the US government: African, European, Asian, Native American, and Oceanian. This categorization is called K5. The overall question here is whether or how this new notion of race matters. On the one hand, it seems that it could help us discover genetic causes of disease. Then again, humans have a terrible habit, which is race essentialism, the reflexive assumption that similarity in apparent ancestry or visible features like skin color and hair texture are grounds for inferring similarities in other things, like personality, morality. Our essentialist tendency is to see a racial classification as a license to infer other traits. So what we're seeing in the faith that race is a way to find genetic explanations for racial disparities in health outcomes is an inference that's of the same form as the other inferences here. And so it better be that we have evidence for that inference and that it's not just automatic. We have to be aware of our racialism, classifying people by race and making inferences from it. Should we try to just get rid of the concept of race? Well, not yet. As long as injustices are done on the basis of race, we need the concept in order to recognize the injustice. However, the consequences of discrimination and oppression are consequences of racial categorization. Biological race is not the same thing as racial categorization. If I'm of African descent, but light enough and with straight enough hair to pass for white, and I'm adopted by a white family unbeknownst to anyone except the adoptive parents, then I'm going to be categorized by other people as white and not subject to the level of police harassment, disadvantage in employment and loan opportunities, and so on, that people classified as Black are, at least in the United States. The biology and the social categorization are two different things. Your biological races on the new view are your memberships in DNA similarity groups, whereas I'm going to use the term racial categorization for the classification your non-geneticist contemporaries give to you. The latter is usually based on visible traits like skin color and hair texture, and on narrative ancestry, which, as we know, may not be the same as biological ancestry. In the new picture, biological races are defined by the results of a pattern-seeking computer program that's applied to the genomes of a reference set of human beings. It identifies clusters of similarity using one or another measure of similarity and difference in DNA. You can ask it to divide the population into 2 clusters, or 3, or 4, 5, 6, 7, 14. And as it happens, it will find a division for each of these. Fans of this view focus on K5, the clusters you get when you ask for 5 groups. So your biological races are the groups among K5 that computer program classifies you as having the right kind of DNA similarity to. And it comes in degrees, so you're going to have a degree in however many you have similarity to. These groups are DNA similarity groups. So why are they referred to as African, European, Asian, American, and Oceanian? That's because the people with the reference genomes that define these sets are independently surmised to have ancestry in these 5 continents, respectively. These DNA similarity groups are correlated with apparent ancestry relations. To get a sense of the correspondence here, let's look at our history as a species. First step, as far as we know, Homo sapiens evolved only once in Africa, in that brown region, about 200,000 years ago. Gradually, subgroups migrated out of Africa and peopled the world. From an ancestral point of view, we're all Africans, even if many of us are also ancestrally other things. The human species is a highly uniform genetic cluster, each member of which is clearly different from those of other species. It's estimated that the DNA from any 2 human beings is 99.9% identical. Also, despite the variation among human populations, there are no subspecies of the human species, as judged by the level of genetic differentiation between populations that is standardly required by zoologists for classifying other mammals into subspecies, which they call races. By that measure, the human species consistently shows up as just one biological race. Anthropologists have used all sorts of empirical evidence and radioactive dating and the sequenced DNA of fossilized skeletons to plot human migrations over time, which gives us some fixed points for mapping our history. The DNA of the current human population adds to our ability to map our past because our DNA is a product of that history. Something worth knowing to get perspective on biological race is that the native African population is far and away the most genetically diverse in the world. To give an example, you can see on this map that there were 7 maternal haplogroups in Africa from the beginning and today. Only one of those made it out of Africa. So the rest of us, all over the world, are descended from that one group. Each population that left Africa was a relatively small one and contained only a little of the genetic variation that there was. It's worth noting that the most genetically diverse population, which is Native African, is going to be the hardest to make true genetic generalizations about, surely. Now this is a map that shows our migrations, and the numbers are times in units of 1,000 years ago. So by about 14,000 years ago, which is over here, when Homo sapiens reached South America, all of the large continents were peopled, even if not to their outer reaches. There was no further continent to go to, so they could only go further within their continent or backwards or stay put. The most recent ice age is ending about 12,000 years ago, so the climate is more hospitable, and there's no longer a footpath over the Bering Strait. So North and South America are separated from the rest of the world. There are oceans between some continents, mountains between others, for example, the Urals. So these populations from about 14,000 to 15,000 years ago largely stayed put, and they increased and multiplied until about 500 years ago, when Europeans started sailing the ocean blue with big ships. In this period of roughly 15,000 years, the populations on the 5 continents had a degree of reproductive isolation from each other, with exceptions and overlap. So members of each of those populations became, on average, a little more like each other and a little less like members of other populations. There was enough differentiation of this sort that a computer program measuring genetic similarity and difference can find 5 clusters that correspond to those continental populations. The separation in this period of time is thought to be the explanation of the structure at K5. I have to say, though it makes sense in broad strokes, it's not clear to me how much has been done to verify that correspondence, because it is an empirical hypothesis. But anyway, if it is the explanation, then your being a member of a particular K5 race corresponds to being likely to have ancestry from that continent in this time period. The computer program can also identify which of 6 populations you're a member of, and which of 2 and 3 and 4. Why is K5 important? Well, the ancestry, if it matches, but it's also been argued that it has the most variance between the populations. However, by another measure, K7 has the most variance between populations. So all these DNA similarity sets, K7, K6, and so on, are in one way or other a trail of our ancestors' reproductive interaction and lack of interaction. You might be surprised that this is all there is to being a member of a biological race in the new sense, being a member of a DNA similarity class. If so, then it may be that your essentialism is showing. Several times when I've spouted my 23andMe DNA ancestry results, people have told me, oh, that 23andMe is a scam. All they do is compare your DNA to other people and populations and use statistics. And I think, what were they expecting genetic ancestry identification to be doing? Should 23andMe be comparing me to the essence of, comparing my DNA to the essence of Polishness? All we have is empirical knowledge of DNA, of reference populations, whose location at a given time is known or can be extrapolated statistically, and the ability to compare my DNA to those. And people, DNA, similarities and differences in DNA measured in a variety of possible ways relations of ancestry between people, like who's your mama, and locations of people at given times, these are simply all there is to make a notion of biological race out of. So is biological race relevant to medicine? If you thought it couldn't be because the 5 continental races correspond to nothing biological, then you'd be wrong. But that the new notion could be relevant does not say that it will be a fruitful tool for medicine. What we have in what I've said is that there's enough genetic difference between 5 DNA similarity clusters to classify a person into one or more of the 5. That alone doesn't give us any insight at all into whether there's enough genetic difference to explain differences in disease risk between races. The only way this question can be answered is empirically, and that requires a lot of work and resources. I'm going to suggest that we resist the biological race hype here, but the first thing I want to say is that doesn't mean that we should reject the role of genetics in health and disease. But biological race and genetics are 2 different things. Genetics does help us map our ancestry, but race hasn't too often figured in diseases we've discovered to be genetically conditioned. The poster child for a genetically caused disease is sickle cell anemia. But the distribution of the sickle cell variant in the human population is not racial. It's geographical. You have a lot of it in places where there's a lot of malaria, sub-Saharan Africa, parts of the Mediterranean and Middle East, and India. Sickle cell variants spread geographically where there was reproductive interaction and it was advantageous to the bearer. When it did that, it distributed itself over 3 races in the diagram, in both the biological and the social sense of race, and in a few more populations and races that aren't in that picture. Given this distribution, it's true that you're probably not going to find the sickle cell variant in someone of 100% Native Alaskan descent. That's useful to know, I guess. But genetics is not the same thing as race. It's worthwhile to do research about the genetics of disease. But what about looking for genetic differences between races to explain health disparities? I think there are reasons for skepticism, and I'm about to describe 3 of them. One is that the subtraction style of argument that is used for this is bankrupt. The second is that the direct arguments have had remarkably little success for all the investment that has been put into them. And third, it's startling how misleading some of the presentations of this research are. So a common argument style in this research, at least up to 2018, is a subtraction argument. You look at the disparity in health outcome between races, control for socioeconomic status, and infer that the remaining difference in the outcomes is due to genetics. Now, a subtraction argument requires that you've controlled for all factors except genetics, including, for example, the contribution of social factors like racism. Researchers often still take socioeconomic status, income, education, occupation, as measuring all of that. The problem is that socioeconomic status does not exhaust the effects of racial categorization on health. Just ask Henry Louis Gates, Jr. and Christian Cooper. Gates, a Harvard professor, was arrested at his own front door when he asked for the badge number of the police officer who accosted him as he was trying to get into his house, and who then kept pressing the matter after Gates had shown his ID card with the address on it. It took 5 days to get those charges dropped. If you don't know the story of Christian Cooper, I'm happy to tell you. It's a similar thing. If experiencing incidents like this doesn't raise your blood pressure, I don't know what would. And these are not isolated events, but regular occurrences for Black people in America. High socioeconomic status didn't protect these people from it. Okay, end of the indirect method. Now for the direct method of showing that genetic differences explain health disparities between races. For this, you find disease-associated genes and make measurements of their causal contribution to the disease and measurements of their differential distribution over races. Then you do the math to see how much difference in outcomes is due to that difference in genes. That makes sense, though it sounds easier than it is because causes often aren't additive in their effects. But this paradigm has fallen far short of its promise. Here I'm just citing an authority, but after 30 years, at least $90 billion, examination of millions of genes and hundreds of thousands of full genome scans, the contribution of genetic factors to health disparities between races is generously estimated at 3%. One big reason for this is the obvious fact is that the role of genes in disease is typically complex, with more than one gene contributing in more than one way and combining with environment. You have to wonder what is keeping this paradigm alive. The one success story as of 2018, maybe there are new ones since then, is the discovery of the APOL1 gene, which is associated with kidney disease and only found in people with recent African ancestry. Here's what the researchers say about it. The APOL1 risk variants account for a substantial portion of the increased kidney risk in African Americans. Rates of many types of severe kidney disease are much higher in Blacks than most other groups. Much of this disparity can now be attributed to genetic variants in the APOL1 gene, etc. And again, these variants explained a surprisingly large fraction of this major health disparity. Again, African Americans develop kidney failure at rates 4 to 5 times higher than Americans of European descent. The variants explained a large fraction of this major health disparity. Now, this sounds to me like we have an explanation of a large fraction of the disparity between African Americans and whites in kidney health. All those statements cite this article, which says, in summary, we have shown that sequence variation in APOL1 contributes to the increased risk of renal disease in African Americans. But this article doesn't contain even a reference to data about other races' kidney rates, so it can't possibly say anything about that disparity. In fact, what this gene explains is a big disparity within the African American population. You can find information about the disparity between whites and Blacks, and here are 2 charts about it. You can see that there's a big difference in outcomes between Blacks who have 2 copies of this gene and Blacks who have either 0 or 1. But notice the bigger difference between Blacks who have 0 or 1 copy, the low-risk Blacks, with whites. So that's that difference. Now, people with 2 copies of APOL1 are only about 15% of the African American population. So the average African American's risk is much closer to the low risk, the Black low risk line, which is about like the orange line. That means that this gene explains a tiny fraction of the disparity between Black and white Americans, the part between the orange line and the low risk line. Our previous, whereas the difference is between the orange line and that white line over there. Our previous skeptical authors analyzed this case and estimated it at 3%. Now, it's great that they found this gene, and it's helping them understand the mechanism of kidney disease in some people, and so how to treat it. All great. But the genes explain the health disparities between Blacks and whites in America does not seem to be supported by the evidence. And look how easily we fool ourselves about that. Okay, one last point I want to make. To put biological race in perspective in the clinical context, we should ask whether race is a causal variable, something that makes things happen. Our 2 different race concepts give 2 different answers to this question. Biological race is not a clinically relevant causal variable, I submit. But social racial categorization is a potent causal variable. So what do I mean by this? Here's a causal graph where health and disease are the effects of lots of other things, including a person's environment and their genes. Suppose person A has just one biological race. This race is her membership in a DNA similarity class of individuals. Membership in a group is not a cause, but I'm going to be generous and say that her race is a fact in her ancestry, which is the brown box up here in the upper left. A's ancestry, together with the environment, causes her to have the genome she has on the upper left in blue genes. The causal power of A's biological race is completely exhausted by its contribution to A's genome. Suppose she came into existence full-blown yesterday and had no ancestry at all. If she had those genes, she would have the associated disease risk. A person's genome is a clinically relevant causal variable. Her biological race is not. It's screened off. Racial categorization, on the other hand, is a potent causal variable. This is the rust-colored oval in the middle. It makes things happen. Being categorized as Black can make you get paid less at work, get more exposure to environmental toxins, and more harassment by police. All of those things can affect your health. Social racial categorization is usually made on the basis of visible traits and narrative ancestry, as we said. And it's not genetic at all in the following sense. If you were biologically ancestrally white only, but because of visible traits and narrative ancestry got classified as Black, then you'd experience the disadvantage that comes from that classification as Black. Your genes wouldn't save you from that. So my final word is this. The things in the white box are known mechanisms through which racial categorization causes health disparities between races, and resources addressing those things will definitely be well spent. Okay, thank you. That's it.